The confidence interval formula to estimate the difference in two population means is given by the difference in the y-bars plus or minus a t critical point times the standard error, which is s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. Now the s's are the standard deviations from the two samples, the n's are the sample sizes, and you're going to have to square the standard deviations. Now we're going to perform a lot of the estimation either on the computer using StatCrunch or using part of StatCrunch output, or you'll be given things like the critical point to use or the standard deviations or what not to use. So let's look at some examples. Now first, you're going to want to be careful to make sure you're keeping track of what you're calling the first group or first sample and the second group. So from the general notation, you probably want to change the subscripts in your notes from 1s and 2s to some type of abbreviation that will relate back to what's in the scenario. So suppose in the first example, we're interested in estimating the difference between men and women in terms of mean diastolic blood pressure. A random sample of 16 males and 13 females were examined for diastolic blood pressure. This data was analyzed in StatCrunch, and we'll look at that output. You can assume diastolic blood pressure readings are thought to be normally distributed for each of the genders. And what we want to do is calculate and interpret a 99% confidence interval for basically mu1 minus mu2, the difference in mean diastolic blood pressures for men and women. Now with the data in StatCrunch or in like an Excel file where you've got it in two columns, you'd go under the stat menu to T-stats, then to what's called toSample. toSample means independent samples, and then you would have the raw data, okay, with data, and then sample 1 you'd choose males, sample 2 for females for this output. Make sure this pull variance box is not checked. Okay, that would change the formula that it uses. So make sure that is empty. And then since we're doing estimation, we want a confidence interval. So click in the little circle next to confidence interval, and then make sure the level that you want is appropriate. So if we want 99%, we're going to type in 0.99, and then we would click compute. The output for the 99% confidence interval will tell you that mu1 is for the mean of males, mu2 is the mean of females. So you can tell the order that it was done in, and it tells you mu1 minus mu2 is the difference between the two means without pooled variances, which is what we want. So then in the table you can see the sample difference. The 6.30 would be the difference in the two y-bars. The standard error is the square root of the two ratios of sample standard deviation squared to sample sizes. Degrees of freedom 24. Ultimately the output comes out giving us a lower limit of negative 2.94 and an upper limit of 15.53. But let's look at this a little more carefully. So what I've done is rewritten the descriptive statistics. You've got the sample sizes, the means, and the standard deviations. I also copied down the confidence interval for us. Now the critical point to use for 99% confidence when the degrees of freedom is 24 is 2.797. So what we would want to do is take the difference in the two y-bars. Y-bar in this case for males minus y-bar for females would be the 77.38 minus 71.08. Plus or minus your critical point, your t-score, is 2.797 times the square root of, and then you do the standard deviation squared over sample size. 8.35 squared over 16 plus 9.22 squared over 13. So that ends up giving you, when you round off, something that goes from about negative 2.93 to 15.53. Now that only differs because of round off error. because our standard deviations above, we round it off to the hundredths digit, whereas in StatCrunch it's going to keep it to a lot more digits. So that's what's producing the slight difference between the negative 2.93 and the negative 2.94, but the 15.53 matches exactly when we round to the hundredths digit. So now let's focus on what these numbers tell us, and this is where people sometimes have to slow down, really think about this is the answer to a subtraction problem, and the order that you're taking the difference in is going to tell which is larger or smaller in different cases. So let's think about that very carefully. So we're going to use the negative 2.94 to 15.53 value and then think about what each of these endpoints tells us. So negative 2.94 is the answer to mu for males minus mu for females, okay, at the one extreme end, at the negative 2.94 end. So what does that tell you? Well, if you do a subtraction between two numbers and you get a negative result, it means the first number is smaller or the second number is larger. Okay, so this would mean the mean diastolic blood pressure for females, which was the second number, is 2.94 millimeters of mercury more or larger than it is for males. Now consider the other endpoint, the 15.53. In this case, if I do a subtraction between two values, right, mu males minus mu females, if that equals 15.53, that tells me the first number, mu for males, is that much, 15.53, larger than the other number, mu for females. So that would just imply that the mean diastolic blood pressure for males is 15.53 millimeters of mercury more than it is for females. Or it could be anything in between those two extremes. Now if you think from a negative number to a positive number, 0 is contained in that interval. And if you subtract two numbers and you get 0, that tells you what? Well, that tells you the two values are the same, right? 5 minus 5 equals 0 because 5 equals 5. So I go from, oh, it looks like females might have a larger mean, to they could be equal, to males might have a larger mean. So in this case, because we're doing a confidence interval and it goes from a negative to a positive, we can't tell which of the two numbers is really larger because it could be anything in that range. So the way that you might interpret this is to say, you know, at 99% confidence, it's not really clear whether males or females have the higher mean diastolic blood pressure. Okay, if the males have the higher mean diastolic blood pressure, okay, then it's by no more than 15.53 millimeters of mercury more than the mean for females. But on the other hand, if it's the females who have a higher mean diastolic blood pressure, it is by no more than 2.94 millimeters of mercury. So here's some general observations about interpreting intervals. Okay, in this example, the interval went from a negative to a positive. Okay, or if you want to put the 0 in between, it went from negative to possibly 0 to positive. Okay, so if the difference between the two numbers could be 0, that means they're the same. So it goes from saying one is larger to they could be the same to the other one is larger. In these types of intervals, a lot of times the easiest thing to do is to go with a three-sentence interpretation that just says, okay, at whatever the level of confidence is, it's not really clear which of the two groups has the larger mean. If the first mean is larger, it's by no more than, and that would be your positive endpoint of the interval. If the second mean is larger, it's by no more than, and that would just be the absolute value of the negatives, because you don't want to put a negative number in an interpretation but that would be the value you'd give for the second mean being larger. Or you could say something like, at 99% confidence, it's not clear which mean is larger, but the mean for, the first group could be anywhere from this much less to this much more than the other one. Okay, sometimes that makes sense. Sometimes it's a little hard to keep that straight. Okay, but this is the first example of confidence interval for the difference in means when you have two independent samples. Now, as far as the steps for a confidence interval, what you want to do, okay, is to make sure you define what it is you're trying to estimate, right? Now, in this case, with independent samples, a lot of times it's easier to define the two means separately and then say, I'm trying to find the answer to this one minus this other one. Give the formula you would use in your interval calculation. Okay, that's just your, y bar 1 minus y bar 2 plus or minus your t-score times that square root. Go ahead and calculate the interval. Okay, now sometimes you may be provided the interval and not have to do this. If you have access to StatCrunch, you could put the numbers in there and do the calculation. But you need to practice this by hand a little bit also. Be sure you interpret the interval, and that's where you're going to have to sit back and think, okay, if I get a negative number, okay, what does that tell me? If I get a positive number, what's that tell me? And then be able to determine if the estimate is valid or not. Okay, so what would our solution look like in this case? Well, defining the parameter, we would say mu sub male minus mu sub female is the difference between the mean diastolic blood pressure for all males and the mean diastolic blood pressure for all females. Keep in mind, in mathematics, the word difference implies the answer to a subtraction problem. Give the formula and calculate the interval, right? So I might say, okay, let 1 be males and 2 be females, then write the general formula, and that equals, and then I just read the output from StatCrunch, negative 2.94 to positive 15.53. And then you would want to write your interpretation. Now, you're probably going to, write down a couple of things on your paper before you really type this out. But in this case, this would just be the interpretation that we worked through and eventually came up with when we were interpreting the interval earlier. And then if asked, determine if the estimate is valid or not, right? So the idea is you got two independent samples. Okay, apply sort of what you did in the one sample case, just do it twice now. So we have a random sample of males and another independently collected random sample of females who were measured for the quantitative variable diastolic blood pressures. Each population of blood pressure measurements is normally distributed. So I have normal distributions to start with. And that was just stated in the problem. And then the population standard deviation is unknown for each of the two groups, right? So neither of the population standard deviations is known, neither sigma value is known. So I'm going to use the sample standard deviations in all of the inference.